and we will continue with the topic of myths and truths about quantum computing. And I have a great pleasure to welcome today 4 speakers that will help me to discuss where we stand in quantum computing development, what different platforms we have. There was already a question, is there anything, where do we stand apart from superconducting qubits? And yeah, I'm very happy to welcome here today Dr. Robert Axmann. He's a director of Quantum Computing Initiative from the German Aerospace Center. And he studied aerospace engineering in München, and he also holds a degree in business administration. And since 2021, he is a head of Quantum Computing Initiative. Robert, it's a pleasure to have you here. Welcome on stage.
Thank you very much.
And the next speaker represents one of the very promising startups on the German scene at the moment, Professor Dr. Christof Wunderlich. He's a founder and a CSO of Electron, and he holds a chair in experimental physics at the University of Siegen in Germany. And he founded Electron 3 years ago at the moment. And the startup is focusing on development of freely programmable, scalable quantum computers. Welcome, Christof. It's a pleasure to have you here as well. Please take a place wherever you like.
Thank you very much.
And the third speaker that we have today is Dirk Zechiel. He's a CEO of Quantagonia. And Quantagonia is a quantum software company. They offer in hybrid quantum classical solutions and machine learning, as I understand, mostly in machine learning and AI technology for optimization and simulation. Welcome, Dirk.
Thank you.
And last but surely not least, Dr. Jana Lehner, Chief Business Officer of Quantum Brilliance, which is a German-Australian company for full-stack space temperature quantum computers based on diamonds. She holds a PhD in theoretical quantum optics and has worked in various research groups and has also many years' experience in business operations, consulting, and software engineering. Welcome, Jana. Please take a place on stage. I hope we have enough. So, welcome again. As I said, it's a great pleasure to have you both here, and we have a very broad representation, I think, what concerns quantum ecosystem and quantum landscape in Germany and also globally. And my first question would probably go back to Michael's presentation. What is your favorite myth about quantum computing? What is the fiction statement that you want to address today?
I can start, yeah?
Yeah, please.
So for me, the biggest myth is that quantum computing will solve the biggest and greatest problems. So at the end, as Michael said in his talk, it's one element in solving the problem. It's not the quantum computer itself. And the second point is we are creating the problems and we are solving the problems. And even with the best quantum computer, it's our responsibility to use them best.
Thank you.
Yeah, one thing I often hear, quantum computing will not work. Yeah, it's a little bit funny for us because I think we all believe in quantum computing, and I believe as well in it. And I think it's more an engineering thing, so that it will work in the future. And companies like Electron are working on it to get quantum computers here in Germany up and running. And I think that will happen pretty soon.
So it's a vision, as said, not a fiction in this sense.
Exactly.
Thank you. Robert, would you like to add up on
of
this?
course, yes. I agree on what Jana said. Quantum computing will be, I think, another tool to solve certain mathematical defined problems, and we do see that algorithms are invented, like Shor's algorithm in '94. We didn't know about it before, and it will be something like classical computing, neuromorphic computing, analog computing. It will be another tool being capable of solving very specific problems, and we won't see, at the moment, we expect that we won't see quantum computers in every private household, but it will be a specific tool for certain problems in the future.
Thank you. Are there any additional myths?
Yeah, so
Christof?
let me amend this maybe by pointing out there exist various platforms for quantum computing, physical platforms, and one of the myths is that it's already decided which platforms are going to prevail in the end, let's say. So I think there are a number of many successful platforms, or a number of platforms that are really successful, and all of them face still serious challenges. And so the race for the real platform that is going to give us a real quantum advantage is still open, and it might change during time.
So I would like to directly go for this question. So as you mentioned, there are many quantum platforms under development at the moment. We have Diamonds here, we have Electron with its platform. But my question goes to Robert. Can you maybe give a little overview because I think from the perspective of quantum computing initiative from the DLR, you do have a great overview of what's going on the market. So what are probably the most promising platforms, and which of them are being currently developed in Germany?
The most promising platforms, of course, it's an ongoing discussion. What's the most promising platform? I think in Germany overall, we do develop on all the different relevant systems in quantum computing, so the different qubit platforms. We have activities in the area of superconducting qubits, in the area of ion traps, for example. We as DLR concentrate mainly on ion traps, color centers, photonic systems, based on our analysis of the market. But of course, we have also projects financed by other ministries in Germany. Superconducting platforms are, of course, well established already on the market, like ion traps, with different pros and cons in the different platforms. And I do see that we have a broad coverage of the different technologies in quantum computing in Germany.
So maybe we go then specifically to these platforms you already addressed. Christof, can you maybe talk about what platform the Electron is working, why, and maybe a little bit on the technology readiness of these systems?
Yes, so Electron concentrates on using individual trapped ions, so individual atoms as quantum bits, as qubits. And why is this useful? I mean, individual atoms are always perfectly identical. They are given by nature to us, and no matter if you use them here or on the moon, they are always perfect qubits already. So you only, in quotes, need to classically control them. So you don't have to manufacture qubits. Nature gives them already. And trapped ions have been extremely successful in demonstrating all the ingredients for quantum computing, high fidelity gates, error correction, all kinds of highly interesting stuff, full quantum algorithms and so on. One drawback that's often seen with trapped ions is the control of like I said, the classical control of the qubits using laser light. And so this is actually a very demanding task. So if you want to, just an example, if you want 1 second coherence time of your qubit, you need a laser field that has a stability of frequency stability of 1 part in 10 to the 14, let's say. So this is a small number. It's 1 part in 100 trillionths frequency stability. And this is possible, of course. So this has been demonstrated and is state of the art. But when you think about scaling up a quantum computer, this is still a hurdle to generate such light fields and to bring them to the place where the qubits are. So Electron chose to go a different path. We control qubits by microwave radiation. So we use, like in your mobile phone, you have microwave signal generators and antennas, amplifiers. It's all in a small piece of technology that a 5-year-old can use. So, and it has been proven that it's scalable microwave technology. So yeah, so that's our approach in a nutshell.
Can you maybe say a little bit about the timeline? So, as I understood, you started 3 years ago with Electron. So, when do you imagine maybe to have prototypes or solutions ready?
Okay, I mean, one has to emphasize, yeah, Electron was founded 3 years ago, but the research behind it started 20 years ago. So, so Electron builds on results of a large community of scientists, and in particular also on our own expertise in academia. So, so Electron is kind of a natural continuation of what has been done in science so far, in fundamental science. And so our roadmap, I mean, together with DLR, we are happy to have next year a first quantum computer ready for end users who can play with it, and DLR is going to be the first end user, of course. So there, yeah, we have fantastic scientific collaborations already that are starting now in view of using these quantum computers starting next year.
So it's a very exciting case of transfer from research to actually applications, to technology and applications.
Yeah.
Jana, can you maybe also speak about the diamond-based technology? How is it different? How is your approach different? And maybe, yeah, what is in terms of applications? How does it differ from the other systems?
Yeah, so our diamond technology is based on synthetic diamonds. They have the very good advantage that diamond is a very hard material. Was that all the disturbances that other quantum technologies facing are already solved in a way, so the vibration and so on. And that means we do not need an entire cooling around this, but the diamond itself plus the technology for addressing the qubits and the readouts. So this is a huge advantage, and it also shows the big potential of the diamond-based technology. It can be miniaturized and has a complete different and extended range of application. So that's the high potential. Of course, it does not come for granted. There are challenges for placing the qubits in the diamond. So in our case, we use NV centers in a deterministic way. That is one of the bigger challenge. And also there's a challenge when we want to miniaturize, shrinking down also the entire electronics around the readout technology and the addressing. And these are the two main challenges for the diamond technology to come then to show the full potential. Technology readiness level. Yeah, so the ultimate goal is to integrate diamond quantum computing as a chip somewhere in any kind of devices. So that's the long-term goal, so that we can then apply the diamond quantum computing as part of a bigger compute system wherever it makes sense. And the big potential is to have it also in mobile devices, as we don't need the cooling. And so here, this is the goal. This is still a bit far away. So on one hand, the technology itself needs to be developed. That is, diamond started quite late compared to superconducting qubit. So we are still a bit ahead, late to, not too late, but we are not
behind,
that behind. And that's one thing, to get the diamond quantum computer as a full device, but the more challenging one is transferring it into production, adopting the processes that are already available for semiconductor industry, and this is then really make it ready for as a technology. And this is still a few years to go. It's not really known how many, but for the quantum computing itself as demonstration, that's within the next years definitely feasible.
Dirk, now a question to you, because you as a software development company, you work with different quantum platforms, I can imagine. So can you tell a little bit about your approach and how do you work on this field between quantum and classical?
Yeah, so with Quantagonia, we are trying to hide away the complexity of quantum computing. Because when I first wanted to write my first optimization problem for a quantum chip, I failed. I gave up after 20 minutes, even though I thought I'm a good programmer. I tried, all the complexity with gates and circuits and all that stuff, I wasn't used to it. And so I thought, so there must be an easier way for developers to run their code on a quantum computer. And that's why we are abstracting that so that you can put the code on our platform and the compiler and various technologies decide where to execute it best, be it on a CPU or GPU, FPGA for acceleration, or on a quantum chip. And yeah, we already discussed different technologies for platforms for quantum computers. And that's also a challenge today, because as a business, an enterprise, if you would like to work with a quantum technology now, where do you start? Do you start with an annealer, diamond, ion trap? And that's why we built a platform so that you can put your problems on that platform and we abstract away the quantum technology.
So at the end, the end user doesn't really know doesn't need to understand the difference between the platforms.
Exactly.
That's
like
the
today,
vision
so
at least,
I remember 20 years ago, I knew exactly what kind of processor I had in my computer. Was it a Pentium or x86 or AMD, Intel? And today you have your laptop. Some people know it's an M1 because it's Apple. Others know it's Intel chip, and that's the goal.
And speaking about the user perspective, how does each of you understands the goal in terms of user applications? How do you understand the infamous quantum advantage or quantum utility? I think someone already mentioned today. What is it for you? How do you understand this? Or from your cooperation with users, how do they understand it? That would be also very interesting. What is our ultimate goals? Because that's basically what we want users to have at the end. So
the ultimate goal would be quantum advantage, but today we should talk more about quantum benefit or quantum utility to get. So I think it's already an improvement if we get 30, 50% speed up compared to current methods we are using to solve problems. That would already be a benefit, and we shouldn't look too much into that quantum advantage. That's a few years ago, I think, and look what can we achieve in short term with quantum utility.
What would be the difference exactly between the both?
Yeah, quantum advantage, as far as I know, it's you have one algorithm or one method outperforming any algorithm on classical hardware. And quantum utility, someone brought up that term recently. I see it more like you have some benefit with quantum technology to solve things faster than you do currently.
I would like to just continue. So in my eyes, the first step is definitely quantum utility, because it provides you a measure that is really practical. So it means that for a device that is comparable in size and weight and energy consumption with a classical device, and gives you a better solution that could be faster, more accurate, or if it's fast and accurate, it's also in terms of energy saving better. And this is a definition you can apply to any device from the desktop computer up to also the HPC computers, and the focus is more on the practical application. And with quantum utility, we have then the first indication that it really makes sense to integrate quantum computers in our compute landscape. And so developing business application that create also a commercial advantage and commercial impact. So quantum utility, I think, is the near term, definitely the goal. Quantum advantage has it's also its relevance, but it has a different focus, and is more on, in my understanding, more on the bigger picture, on a complete different view of the problem. Quantum utility, I think, as it is more practical and also more in the comparison, the direct comparison with computing today, is easier and faster achievable than quantum advantage.
You would like to add something, Christof?
Yes, maybe. So actually, I'm not sure if there exist rigorous definitions of these terms that we use, quantum advantage, utility, and benefit. So I think what's really important from a user side is exactly what you said. the user needs to see some advantage, why should he or she use a quantum computer? That's the key point. And this advantage doesn't have to be an exponential advantage like in solving Shor's algorithm. This can be an advantage in simply with a constant factor. Even a factor 2 could be relevant for real application, a factor 2 in time or energy consumption. I mean, if you think about supercomputers that consume the power of a small town, a factor of 2 matters if you can reduce for certain problem the power consumption or the time you need. So there are time critical applications where it's relevant if you spend 10 seconds or 20 seconds on a task. And if an imperfect quantum computer can solve a task in 10 seconds instead of 20 seconds, it might be relevant for logistics applications and stuff like that. So, yeah. So we should be more modest. We shouldn't expect in the near term exponential advantage of a quantum computer. I think even applications that give us a constant factor in speed up or energy consumption would be great to have.
And you mentioned already specific areas of application. So where do you see the ion trap platform can bring, in which specific types of problems can these platforms bring this utility, whatever we call it? In the at first, I would not say like in the next couple of years, but as first.
Yes, so maybe I'd like to introduce a different notion also. So when we talk about quantum computing, there are different approaches within quantum computing, and one of them is quantum annealing, actually. And quantum annealing has been under large debate whether it's actually advantageous or not, but there are proven instances where quantum annealing helped to give some benefit to users. So, okay, let's put it this way. And I think quantum annealing could be one of the instances that really give a benefit to users in the near term. And there exist, of course, great quantum annealers already, but they lack coherence time. So the time during which you keep the quantum aspects really alive. And I think it would be a great improvement to really have a coherent quantum annealer that really takes advantage of quantum effects during its whole application. So I just like to draw the attention to such problems. Other problems are widely discussed, like variational quantum algorithms and stuff like that. So they are also expected to be very beneficial in the not-so-distant future, especially coupling them with high-performance classical computing. So, yeah, so that's where I see lots of benefits, potential benefits. Yeah.
And Robert, Christof has mentioned before that the built-in quantum computers, but also the other companies that were supported by DLR and BMWK, and he mentioned that DLR would be the first user of these quantum computers. Yeah. Can you elaborate how you're going to use it?
Well, we started already different projects in the area of using the quantum computer. So we are focusing on different problems relevant for our research, but also relevant for industry. And for example, we talked about the quantum advantage or quantum utility. It's not just to be faster. It's, of course, also the energy efficiency, for example, for quantum machine learning, QML, where we think about, might there be a benefit in the future if we are going to train large models, climate models, whatever, large language models. They are continuously growing in size, and they are doubling the energy consumption and the compute power, and that might be of course, an answer to have quantum computers at least to support simulation of those models. And we do have other problems like the gate assignment problems Michael talked in the presentation before, but also problems in the area of simulating quantum system itself, cryptographic problems. So there's a variety of problems we are analyzing at the moment, and how do those problems perform on the different platforms we have at the moment, because it might be in the future that we see that different platforms perform differently with different problems.
Yeah. I would like to go back to you, Dirk. You're also founder of Gurobi company that is focusing on optimization, specifically on optimization problems. And Christof already mentioned it, the relevance for logistical situations, problems. Can you maybe elaborate? You focus specifically on this optimization with Quantagonia, or are there also other areas where you see the big advantage?
Yeah, we started with optimization, but we're also focusing on simulation and machine learning. But there's a lot of potential in optimization. Every company is already doing optimization, but to give you an example, for example, in energy trading, in Europe, the electrical power is traded in 15-minute windows. And if the energy companies could make a better decision within these 15 minutes, if they should produce energy, buy energy, or sell energy, there's much more efficiency in terms of revenues, but also energy efficiency in the end. Or transport and logistics, imagine if you can schedule your trucks much better on the roads, you save a lot of fuel. There's a lot of potential, and they are all seeking for speed, especially if you would like to make real-time decisions. Take a train schedule, it takes weeks to create a train schedule because of the complexity for your network. But if a train is blocking the track between Hamburg and Hanover, you would like to press a button and get a new schedule for the afternoon, and not being on the television in the evening. Yeah? And all these models, they need more power, more speed, and that's why they are looking for quantum chips for the future.
Thank you very much. Jana, you mentioned you work on the mobile solutions for quantum computing, and you developed a full stack quantum system. So what applications are you focusing in specifically? Maybe you can give one example, if possible, in specific industry.
Oh, well, that's a very difficult question to say. This is the first one. As the ultimate goal is really the mobile quantum chip that can be integrated everywhere. And so potentially it has applications in every industry, in every branch. And if you look at quantum computing as accelerators, then even then it has a lot more potential. And as Christof already said, even factor 2, which is already 50% more, so 100% more, then this has a huge impact, and it can, with AI, for instance, being everywhere in combination with AI, really have a big benefit in a lot of problems. With the additional mobile one, it can be maybe also dynamically solve optimization problems in logistics systems that are some very huge, I don't know, I missed the word. Well, where all the stuff is stored, it can have here and there. The first application, so as we are still moving to the past to be mobile, certainly is to start with the integration. Wherever we place the quantum computer, it is an integration problem, integration into existing infrastructure, processes, and also technology we may be replacing. And this integration is the biggest task for today. And the best testbed for integration are HPC. They are existing. We can integrate the quantum computer and learn about how these two systems talk to each other and benefit as a preparation for going to wider industry. Examples for potential applications are all independent devices like mobile cars, satellites or so, but this is still a bit away, but potentially they may have problems that are interesting and possibly also solvable with quantum computers, quantum accelerators in the near term. And so probably this would be, but I would not limit on this. So this
Yeah, sure. I mean, it's very difficult to make predictions at the moment. So my question was, I believe, very difficult for both of you to say very specifically. But I would like, I think we saw now that we have a very broad range of technologies being currently developed in Germany, and it feels like Germany has a very good stand-in now in the international landscape. And Robert, I think you know it probably better than anyone else. Can you maybe tell a bit what are the hubs of quantum computing worldwide? What are the main, I would say, competitors for Germany or players apart from Germany? And how does it compare our current ecosystem on the international, maybe European level as well?
Well, I think most of us see also Northern America. It's very active in quantum computing. Yes, so the States, of course, but Canada also, and we do see a lot of activity in Australia also, and then Asia, Japan, Korea, China. It's a move for me. So I don't know what's really going on, but I think they are very active. And if we do have a look at Europe, for me it's usually we do have to look at the Netherlands. Very active, France, of course. Austria is very active. The UK, and then of course Germany. And if we, or my view at least, is that we, with our governmental programs, with the Ministry of Economy, Ministry of Science, and all the other agencies very active in Germany, we showed up on the landscape within the last 3 years. So we did a good start with our ecosystem, and our ecosystem covers the whole stack. So we do have Christof with producing hardware, Jana producing hardware, Dirk in the area of software. So we have software applications and the entire chain of the ecosystem in Germany. So we did a good start, and I think what it needs now, it's continuity in Germany to go on, because we do have a good basis in the fundamental science, and we do have a good landscape of startups. And now it's important that we go on with this, what we started already, and to go on with what's feared by the others, maybe, that Germany is now also in the game. So that's my point of view.
Yeah, I think it's also appeal to the federal government that probably are not present here yet, that we will to support this continuity and not to disappear from this landscape in a couple of years. That would be probably our wish for everybody.
May I compliment what Robert just said? So when you ask about how does German efforts and European efforts, how do they compare to other places in the world? So as far as startups are concerned, so first a remark, building a quantum computer cannot be done in a research setting, not at a university, not at a research institute. Really, you need an industrial setting for this. Also, Michael Förtsch mentioned this before. So we need startups who do this, and if you compare the investment into startups in the rest of the world, like in the US, it was during the past 20 years, it was around $3 billion that were invested in startups. In the UK, about 1 billion. In the EU, in Canada, just 1 billion, and in all of the EU, it was half a billion. So the investment in startups who are supposed to really make a difference in the end, that's still lagging behind. I think governmental programs are great, but then in addition it needs investments in startups.
Private investments.
And it should be a little bit easier. So the number sounds great, 3 billion, but to access the money as a startup, it's really difficult. Because
so that's for the US.
In Milliarden, 3 million. So, but accessing the money or getting the money from a startup perspective is really difficult, because we cannot afford to get into big tenders where we need to put three people on it for a few weeks. And the government should maybe act more like in VC and trying to distribute more the money and getting more risk, and not trying to make every investment 100% secure, successful investment. So that's the VC world. 99% of the investments fail, and the government should maybe take a little bit more risk doing so.
We do have a discussion today, later the day, about the challenges the startups faced while acquiring financement. So I invite you to stay until the end of the day and also hear about this. To wrap up this discussion, this interesting discussion, we made these statements about myths in the beginning. And maybe you could summarize your opinion now, so to have a takeaway message for our audience. If you can say in one sentence, where do we stand today with quantum computing? What would it be?
Yeah, then I to start. I think the original hype and the exaggeration is slowly fading out. We are coming now to a stage where we think about real problems that can be solved with the technology today, and also what we expect in the near future. I think it's good, but we need to continue on this, really thinking about problems that really have business relevance to really create an impact that quantum computing can make. So I think we are just in the transition phase, and we need to keep the momentum to make quantum computing really a part of the compute landscape.
Thank you.
I would say we're on the launch pad now and have the lighter in the hand, and now we should start the rocket. And I can just tell the enterprises they should, work on quantum computing and not like with AI 10 years ago, wait until it's ready. So they should act now and start the rocket. Yeah.
Great. Robert?
To go on with this, I think we left the launch pad already, but we are still seen from the ground. We do have the ecosystem started. We do have a very lively ecosystem at the moment, and I think we should go on with this. And events like this, Bitkom event, for example, we will see more in the future. And this is important that we go on with this, what we started, continuity, to see that we have the quantum advantage, whatever, energy efficiency, more computational speed up, that would be the important factor for the future.
Thank you very much. Christof?
I think we are in extremely exciting times as far as quantum computing is concerned. I mean, real-world applications are in sight now, so within half a decade, I think we will have really interesting real-world applications. And one thing one should mention, so a universal quantum computer is still far away, but we will have real-world applications where quantum computing can contribute something useful, and in order to do that, what we need is, I think, co-design. So software experts and hardware experts have to work to make the best out of existing algorithms and existing hardware to bring these two things together. So that's an important thing, I think. Co-design is the keyword for the next few years.
Thank you. I hope some of you will be encouraged and motivated by these statements, and probably also get engaged in a co-design and development of quantum computing future in Germany. And with this, I thank the speakers here, and we continue the momentum of this program today. Thank you very much for being here and for your contributions. And yes, welcome.
Thank you.